images of what you feel comfortable shooting today or this month in June. And with that, we have tonight's speakers, Doug Summers. I think, Doug, I found you I think you did a last year, 2 years ago, maybe for Tucson. I was watching one of your YouTube videos on it, and I thought, it'd be interesting for this organization to have you join us. Ooh, what happened here? Go back. Is it still sharing?
Yes.
Yep.
Okay. Yeah. So I invited Doug. He did a presentation on the mono versus a one shot, which I thought is interesting. This is, I guess, one of your images I stole there from Astro Bin there for your bio here. But with that, I guess please keep yourself muted. Put your questions in the chat, unless something really you got your itch there you want to ask Doug. But otherwise, let's wait to the end and give Doug your attention here. So let me hit share and turn it over to Doug.
All right, thanks. Let me see if I can share my screen real quick. Right, and wait a minute. So can you see this can you see the screen right now?
Yes.
Great.
Set up his viewer mode. There you go.
Yeah, I changed it.
Okay.
Yeah. Okay, so glad to be here tonight. Maybe by way of quick introduction for those who don't know me. I was a long time, member of the Keck Observatory staff, working high angular resolution projects. I worked there for 11 years and then took the software manager's job at the Large Binocular Telescope and got my feet in the fire quickly. There's 15 focal stations there, all with different instrumentation. And so, that was an interesting experience. And then eventually I retired from the Stewart Observatory in the University of Arizona. And I had been waiting to, I'm a longtime visual observer, but I was waiting to go, do my own astrophotography until after I retired. And so in 2018, I retired and got my own imaging rig, did my own design there, and the rest is history. So I enjoy the technical aspects of these things, and tonight we're gonna delve into a very hotly debated topic, which is mono versus OSC. And so I hope by the end of the talk, folks will have a clearer idea of the trade spaces that are involved here. Because if you just want to take the amount of vitriol that goes back and forth on cloudy nights as an indicator of how evenly balanced these two heavyweight ideas are against each other, the real issues are more subtle. And so hopefully you'll see what the trade spaces are. And for those of you who are still trying to decide, you'll have a better idea of the variables involved so that when you do make your decision, you'll be able to make the best decision you can. Okay, so with that, let's start by talking about what it is that we're fighting over. All right. So if you think about it, a CMOS image sensor, okay, has a micro lens on the top. It's got a photodiode in the middle, and it's got some analog digital readout circuitry on the bottom. All of that for mono and OSC is exactly the same. So the only thing we are fighting over, okay, is the presence or absence and the properties of this color filter, right? Otherwise, everything's the same. So once we understand the differences in those filter characteristics, then we're in a better place to judge which one we'd like. So I'm going to start this talk with some reasons to think twice about mono. I'm not discouraging mono. I'm just going to give you some ideas for why you might want to think twice about it. And at the end of the talk, I'm going to come back and I'm going to give you the reasons why I think you should think about mono. Okay, so I'm going to try and be fair here. So the first reason is that mono workflows are generally less enjoyable. I think, the combination of multiple filters you can automate, but they're more complicated and more things can go wrong. And so this is one, thing to think about with mono. The second one is that it is true that mono is a little more expensive. You've got a delta cost for added filters, a filter wheel. The cameras are a little more expensive, and of course, you're storing more disk files. And so that's something to think about. And then you got to ask yourself the question, is it wavelength isolation that we're trying to do? Because if that's the goal, then technically, although it's pretty inefficient, you can do that with an OSC. There are dual, tri, and quad band filters that will give you the signal wave bands, the narrow band signals that you'd like. But I think there's a couple other thoughts that really kind of stick out. And so the first of those is for those of you who haven't built a system yet, what's the bang for the buck? Okay, I mean, in terms of a rig cost, uh, if you think about mono, it's often used with small apertures and slow optics. Okay, and I'm talking about in the 4-inch aperture regime and f5-ish. Okay, and if you want to compare a system like that, if you go out and build a system like that and compare it to an 8-inch f19 Hyperstar OSC rig, well, you have to think about the signal advantage that's gained by going with the bigger optic and the faster optic. This 27 times. And when you're talking about that, take the square root of that for the SNR, and you're talking about more than 5 times an advantage, okay, and only half the area spot size. And so this is, something to think about, right? We can talk about efficiency, and we will talk about efficiency, but this is a pretty big bump in SNR, depending upon whether you want to go slow and small or big and fast. The other thing I think that's not really talked about much is that mono produces false color for visible wavelengths. And what it's doing is it's giving up color fidelity, okay? And that is mapped colors and fewer hues to promote contrast clarity, okay? And it does that by only having fewer wavelengths that it has to deal with, right? It can, really exaggerate the contrast of that, of those fewer wavelengths. And so this is something to think about, and we'll maybe touch on that a little bit more. Okay, so are there some technical reasons to favor mono over OSC? And where do you go if you want to know, the answer to that? Well, you go to the experts, of course, and those experts are on cloudy nights, right? And so there's 1,000 pages or so of argumentation out there. But if you go out and you try and distill all of those pages and think about what's being said there, what are the technical reasons for not, for not liking one or the other? And the points against OSC kind of fall into three general categories. The first answer you might get if you ask the question, what's wrong with OSC? You'll get an unqualified answer. OSC cannot approach the image quality or efficiency of a mono camera. Well, you'd like something to back that up, okay? And so if you push a little harder, what you typically will get to next is the crowd appeal argument. Well, most people eventually transition to mono from OSC, so that's a good indication that mono must be better. Well, that seems a little unfair because if you think about what happens in the hobby, everyone is told to start with OSC because it's easy and then move to mono. Okay, so that's a little self-fulfilling there and not really satisfying as an answer, as a technical answer. And if that's not good enough for you and you keep pushing, you might get the appeal to authority. Okay, so scientists use monos and filters, and so mono's got to be better, right? Well, I think that's a little bit apples to apples and oranges. Okay, so I wouldn't accept that as an answer. And if you keep digging and keep pushing, eventually you do find the arguments. Okay, and those arguments against OSC tend to come into kind of three major categories. The first argument says that mono yields better resolution, and that is detail, as compared to OSC. Okay, we can test that. The second argument says that mono has more accurate color reconstruction with less noise than OSC. And generally that's based upon the Bayer matrix that's on top of the OSC and its interpolation, the way it reconstructs color. The third argument is that mono is more efficient than OSC. And those arguments kind of break down into three categories. The first one's like 100% of the mono pixels are always working while the OSC is not. The OSC is wasting at least half of his pixels because, there's no green in space. And it would take 3 to 4 times longer to gather the same light as a monocam, again, due to that Bayer filter. And so 3 to 4 times, wow, that's like two f-stops, okay? That's quite an assertion that's being made there. So I'm going to spend most of the time in this talk talking about these three arguments and see if we can put a little meat on the bones and find out where the truths are from where the fictions are, and we'll be in better position to make some judgments. Okay, so let's start with resolution, the first major topic, and just remind ourselves of what that's all about, right? And I'm going to assume a perfect mount, perfect optics, and perfect focus for this, and that allows us to eliminate some variables, all right? So in that context, we can say that the resolution that's coming from our telescope is some function of the optical signal that the telescope is generating, the way we sample that for reconstruction, digital reconstruction, what the atmosphere is doing, and the noise that's that's embedded in that signal. And so here we go. Here's the signal from the telescope, and it's a high frequency signal. And I'm showing you here three views of the same thing, okay? One is a three-dimensional view of an area, all right? You've got 10 microns by 10 microns here, showing a point spread function where the intensity, is peaked in the center. And then you guys may have heard of full width half max. Well, that's the full width at half maximum intensity. And then you've got these lower power wings, okay, that are Fraunhofer diffraction effects. And so this is what our telescope, this is the signal our telescope is giving us. Now here, this is the same image, okay, but it's just God's eye view. And you're seeing the airy disk, okay, here, and the low power wings on the side. And now you've got a cross section cut here, all right, that's not as real, but it's a cartoon, but it gives you kind of some ideas. And I want you to remember that this 1.22 lambda over d, because this is an important piece of information that is going to come back to us later when we need to talk about seeing. So the size of the airy disk in radius, okay, that first big piece, this radius is 1.22 lambda over d, where lambda is the wavelength. Usually green light is a good wavelength to use, and d is the diameter of your optic, okay? So this is our signal that's coming from the optic, and now we need to digitally reconstruct it, right? We need to get it out of optical space, and we need to get it onto our computer screen. And the way we're going to do that is we're going to lay down pixels with some density. And so we're going to put a pixel here and sample the intensity at this location, another pixel for the intensity here, right? You get the picture that we're sampling intensity across the area. Imagine just stacking a bunch of pixels in this area, and we're going to measure the intensities all over that and try and reproduce the signal. If you don't have enough pixels, okay, if you're not sampling with enough, with enough density, then you're going to wind up doing what's called aliasing, right? Aliasing is like the way of producing a different signal that, is supposed to represent the original, but it doesn't. And so here's a case where you can see aliasing in practice. And what's happened here is that we've got a nice cosine function, a high frequency signal, and we're sampling at the peak of one peak, and then down at the trough. Can you guys see my cursor, by the way?
Yes.
Yes.
Okay, great. So at the trough here, but two cycles over and again, over and over and over. And what you can see here is that we are producing, by sampling like that, undersampling, we are producing an alias, a different signal. It's not the same original signal. It's producing a sine wave or a cosine wave, but it's not the original. And you've seen this effect before when you see wheels spinning backwards where cars are going forward and other things. But these aliasing effects are because we're not sampling with enough density to achieve the end goal. Here's a look at a color artifact, okay? Another problem with aliasing, where as the frequency gets higher and higher, i.e. the spacing of these diagonals gets closer and closer, there's a point at which the sampling can't keep up with it, and you wind up getting color effects. These are artifacts. We don't want these in our images, and you don't have it on this side because the sampling's better. Okay, so you may or may not have heard of Harry Nyquist of Bell Labs. He's widely credited with with coming up with a theory about how much you need to sample to accurately reconstruct a high frequency signal. And here, what you can see, I've got three images here. This is a reference image where you've got a single point source and its airy disk. and it's the whole airy pattern. And you've got 3-point sources that are much closer together, and their airy patterns, and what the effects are of sampling improperly and properly. And the first thing you notice is that if you sample 2 pixels over the radius, what you wind up with is an artifact. Not only do you have square, blocky stars, but you get what looks like spider veins, okay? You get these artifacts in your images, and this is purely coming from the fact that you're not sampling properly. You're undersampled here, and so you're getting an artifact. If you instead sample 3 pixels over the radius of the airy disk, you wind up being able to much better reconstruct the original signal. And so undersampling, you get artifacts. And now the question you might ask is, well, okay, let's just not undersample. Well, what if we oversample? Well, the problem with oversampling is you've killed the aliasing. You don't have that problem anymore. But what you have done is you've taken the signal that you had in a smaller number of pixels originally, and now you spread it out over a lot more pixels. So now your signal has come down relative to the prior condition. And so you're lowering your signal to noise ratio, and we don't want that either. We need to strike the balance of finding Goldilocks, right? Not aliasing with undersampling and not losing SNR by oversampling. Okay, so that's the laboratory. We were in the laboratory before. We're just dealing with diffraction, and now we need to start to factor in the effects of seeing. And everybody knows the atmosphere is turbulent, and what we are limited by, we're not diffraction limited anymore, we're seeing limited. Okay, and so everyone should expect that at an amateur site, you're going to be from 1 to 3 arc seconds of seeing, and typically 2 to 3, maybe 2 to 3 plus, okay, is normal. And so when you think about the atmosphere, you need to think about, what's between the deep space object that you're trying to see and your telescope optic can be thought of as a bunch of little cells that are riding across your telescope aperture. This R naught parameter, okay, is a coherence parameter. And what it means is that this is the area, if you will, the size of the seeing cell for a given seeing in arc seconds that is coherent or consistent, right? And so you can imagine in 2, you've got 50 millimeters, in 2.5 is 40. And as you go down in worse seeing conditions, the sizes of the cells get smaller and smaller, and this tears apart your image basically. So if you look at your aperture in inches, all right, and I've shown several from 2 to 11 here, you can see how that is, whoops, hold on, how many cells are floating across the mirror, right? There's quite a few. And by the time you get to 11 inches, you've got 31 little air cells moving across your mirror. And each of them, if you look at the top picture here, what each of those cells is doing is they all have a slightly different focus. They have a slightly different tilt. And so what you wind up with, if you take a high-speed image of the instantaneous moment on your aperture, you wind up with what's called speckles, okay? And so these are different images of the star that are all coming from those different lenses that are crossing your optic in the seeing sense, okay? So you might say to yourself, well, let's not do big apertures, let's do small apertures. Let's stay close to diffraction limited. And then we'll have to deal with less air cells moving across the mirror and making pictures that look like this. All right, well, that doesn't work out because remember that 1.22 lambda over d? That's the radius. Well, 2.44 lambda over d is the diameter. And when you start playing that game, what you see is that if I go diffraction limited with small apertures, 2, 3, or 4, look at the airy disk size. It's bigger than the seeing, okay? If I've got 2 arc seconds seeing, but my airy disk is 5 arc seconds, well, that didn't do me any good at all. I would have been much better off to try and come down this curve and go to the sweet spot, wherever that is. And so now you talk about, okay, well, for bad seeing sites, maybe you go with 4-inch apertures. And for better seeing sites, well, obviously the better the seeing is, the more you can get away with larger and larger apertures. And so hitting that sweet spot is a little bit of a trial and error kind of thing. Okay, so let's talk about imaging scale for a moment. Most of us have seen this before. When we match our telescope to our cameras, we need to get to an arc seconds per pixel that is appropriate. And so what you need to be doing to maximize the performance of your images, and it doesn't matter whether it's mono or OSC, is you need to set up for 3 by 3 pixel grids. Now, I said before that Nyquist was 6 by 6, okay? But that's in a laboratory. When you get out under the sky and seeing is acting as a low pass blurring filter, you can go to 3 by 3. And what that does for you is that's going to give you round stars. Your artifacts are already being blurred because of the low pass blurring filter function of the atmosphere, but you keep your signal to noise ratio as high as possible. You're not giving that up. And so you're finding that sweet spot for sampling. And so in 2 arc second seeing, you should have an image scale that's 0.66. If you know that your best site, that your best seeing at your site is 3 arcseconds, well then 1 arcsecond, 3 by 3, will give you the sampling that you want. If you design it because you think it's one value of seeing at your best, and it turns out to be something else constantly, then you can do a couple things. If it's better than what you expect, you can drizzle. That gives you a little better detail at a cost of oversampling and reducing your signal to noise ratio. If, on the other hand, it's constantly worse than you anticipated, well then, in a worst case scenario, you could bin. And what that means is that you don't have the detail anyways, right? The seeing is not allowing you to get to the detail you want. So you might as well increase your signal to noise ratio and keep it high. All right, so let me give you an example of this. I have a RASA 11. My airy disk size, okay, is 0.9 arcseconds. That's what an 11-inch airy disk size is, and that's the floor. No matter what I do, I'm not going to get a smaller spot than that. And in fact, because of the RASA's design, I don't even quite get that, right? It's closer to 1.5 or 2 than to 0.9. I'm at short focal length, right? I've got 620 millimeters. And from this formula, you can see that if I've got small denominator, I better have a small numerator as well if I want to get down into the low arcseconds per pixel category. And so I would like to do that, except that the smallest pixels I can buy are 2.4 microns. Well, that image scale, if you plug that into the formula, you wind up with 0.8 arcseconds per pixel. That's what I'm sampling at, and that's best suited for 2.4 arcsecond seeing, right? 3 times 8, 24, 2.4 arcsecond seeing. I live near the Continental Divide. I'm at 7,500 feet, and my seeing is always better than 2.4, almost always better. And so I drizzle all the time. Okay, let's put together this resolution thing and see if we can kind of sum up where we've come from. First of all, the scope's airy disk is a performance floor. You're not going to get smaller spots. Big apertures have small airy disks, and that's less than the typical seeing, so you are seeing limited. You can measure the seeing, okay, lots of different ways. One easy way, by the way, is to take your smallest stars, make sure you're sampling at 3 by 3, or look at the stars and see how many pixels. You know what the pixel scale is, so then you can figure out what what you're seeing is. But expect 1 to 3 arcseconds at amateur sites, right? Typically 2 to 3 or more is pretty common. You want 3 by 3 pixels over the best expected seeing. And you want to be 1/3 of that best expected seeing. That's your 3 by 3. Drizzle or bin to adjust as needed. And what you're trading detail for signal to noise ratio, depending upon whether you have more detail and you're willing to give up the signal to noise, or you want more signal to noise because you don't have the detail. Now, we haven't talked a lot about signal to noise. We have talked about it as a function of sampling, undersampling, or oversampling. But of course, sub-exposure times and stacking are your friend, right? You want to basically expose until you right before you saturate, and you want to, of course, get as much integration time as you can and stack those frames. That will increase your SNR. Now, I said we were going to ignore, we were going to assume perfect mounts, perfect optics, and focus. Well, if you want to basically destroy your, your telescope resolution, the easiest way to do that is to be out of focus, be out of collimation, and have a terrible mount. So don't ignore those things, right? Again, we're talking here about peak performance. And so if you want to peak this up, do the best you can to make sure those things are functioning correctly. Now, what didn't I talk about? Guess what? I didn't talk about a Bayer CFA at all, okay? So a Bayer color filter array doesn't impact your luminance resolution at all. That is only a function of the optic, the way you sample that signal, the seeing, and the noise, okay? And so maybe you could argue, well, okay, the noise might play a bigger part in here, and we're going to talk about noise as a function of efficiency in a little bit here. But generally speaking, mono versus OSC is not a matter of luminance resolution. Okay, so now let's switch gears and go to topic number 2 and talk about color reconstruction, because here things get a lot more interesting. We've got a simple camera here, 16 pixels on both sides, and you can see immediately that something's not right here. If you're looking for mono, every single pixel is going to have a direct measurement when you put that red filter on, likewise for green and blue. They're all going to have unique measurements based on having their different filters. But in the one-shot color camera, okay, we don't have that. And so the question becomes, well, how are we going to build this? How are we going to get a value for red, green, and blue for every pixel when all we've got is 4 direct measurements, 8 green measurements, and 4 blue direct measurements? And the way that's done, okay, we need to understand just a little bit about that. So one-shot color cameras go through a debayering process. That's typically done with an interpolation algorithm, and I'm going to describe a VNG, or a variable number of gradients. And how that works is via measurements from the nearest neighbors. So down here, I've got a blue pixel. We have a blue measurement for that because it's a blue pixel. How do I get the red and the green measurements for that? Well, I go to the neighbors, okay? Here's the green neighbors of the blue pixel, and I form a gradient of all 4 of those values, and I use that as the green value in the blue pixel. Likewise, for the red, I look at the neighbors, and I go ahead and I use the gradient value for that red value, so that when I'm done doing that process of debayering and the VNG, I wind up with a measurement for every pixel, red, green, and blue. Now, you can ask yourself a couple questions. Is that interpolation sufficient, okay, and is color resolution decreased as a function of doing that operation? So if we want to talk about resolution, the way this is done in the laboratory, okay, is you put these things on a bench and you subject them to line pairs per millimeter grid, where you have various size bright and dark bands, and they would get progressively smaller and smaller until you can't resolve them anymore. And then you know what the limit of that resolution is. Well, in our case with these cameras, we know what the pixel size is in microns, so we kind of know where the resolution is going to be. I can take a bright band and lay it right down on top of that size perfectly for these pixels, put a bright band here and a dark band here, bright band, dark band, and in fact, I could turn this 90 degrees, this pattern, and I could play the same game in horizontal, bright, dark, and I will come to a resolution that is fixed. Okay. Now, what happens with by the way, the pixels for the OSC are the same size. So you'd say to yourself, well, I can do bright, dark, and play the same game horizontally, and I don't come to the same answer. And the reason why is the interpolation. Remember that when I said we were interpolating, when I have a dark band here, okay, and let's say this is a blue pixel, you can see it here. If I've got this blue pixel and I want to know what the red value is, if I'm doing V and G interpolation, I'm going to take a color gradient of the 4 neighbors, red, and I'm going to assign that red value right here. And we know that's wrong, because what we know we laid down was a black, dark band, and we just put a red value there that's non-zero. And we did the same, we're going to do the same thing for green, and that's not right either. And so it is true that in a laboratory, the color resolution of a one-shot color camera is not as good as a one-shot or as a mono camera. No question about it. But is there a saving grace? And there is. You can dither this pattern, okay? Dithering is just a matter of shifting, if you will, shifting the pattern around on these pixels. And if you do that, you will wind up getting a sub-pixel resolution where you can rebuild without using interpolation at all. You can rebuild the colors to the same specification, to the same resolution that you have in mono, at the cost of some additional exposures and integration time, right? But technically, there's no reason why there's a difference between these cameras. You just have to do another method to get to the same answer. Okay, so there's a money shot in every presentation, and I think I'm about to show you the money shot, but not quite yet. I'm first going to set it up. Here is a 2.4 arcsecond seeing cell, okay? And by the way, I could have used any seeing. I could have used one, I could have used three. But the key here is that whatever seeing I used, I need to make sure that I'm sampling at 3 by 3 because I want 3 by 3 pixel groups when I play this game. And so the method for my madness will become apparent in a minute. But had I used 3 here, I would have used 1 arcsecond per pixel so that I could stay in 3 by 3. Now I've got a nice picture of a red star here, okay? And if I were going to, when you use 3 by 3 grids, there's only 4 patterns in a Bayer array that you have. One of them has 4 reds, one of them has 4 blues, and 2 of them have 2 reds and 2 blues in mixed patterns, and the rest are green pixels, okay? If I wanted to pick, it's kind of a trick question because I can't do that. But if I wanted to pick where I would lay down my red star on top of this grid, where would I go? Well, I would go to the place where I have more red direct measurements because that means I would do less interpolation, right? But like I said, you don't get that option. And so what are your choices? What can you do? Well, one choice is to expand and go to 4 by, whoops, let me go back, to go to 4 by 4 pixel grids instead of 3 by 3. And then I have 4 blues and 4 reds always, but I'm giving up SNR when I do that. And I probably wouldn't prefer to do that. Instead, what can I do? I can play the same game. I can dither. Okay, if I dither, then what I'm doing is I'm moving my star around and averaging over all of my sub-exposures the various measurements that I've taken. And so this spreads the color out. So now the method for my madness, okay, I'm going to show you a video. I'm going to show you a video that I found on the YouTube that basically shows a star taken with a 5-inch telescope and an EOS Canon. And Arcturus is the star, was very bright, but you can think of this as any star. Okay, I'm going to match this up properly. And so there's the 5-inch telescope that was used, and it's playing a live view on the camera. This is a Canon EOS camera live view that we're going to look at. And you're going to see this is not the right scale, okay? We're trying to match up the scales here of our seeing to our star on the grid. There it is, okay? So now you can see what's happening with this star. It's blowing all over. The colors are going everywhere, right? Because you've got color shifting, you've got focus and tilt and all other kinds of speckle behavior that's happening here. Now what I want to do is I'm going to play that again, except now I'm going to show you the transparent overlay. We're going to make it closer, and we're going to ask the question, how much different is any neighboring pixel from the center location where the majority of the energy is? And so we're going to play this again, except now I'm going to control it a little better. I'm going to take you right to the crux of the argument here. There's our airy disk, okay, but when we put it into the presence of seeing, we're going to get this. And now think about, how is any particular piece of this going to be different? Is it going to matter that you've got, that you're taking an interpolated value here for red from these guys or green from here and using it in the middle? And I think, look again, just to make sure that you're convinced yourself, okay? But I'm going to suggest that it doesn't matter, all right? That in general, this interpolation algorithm is going to work out pretty well. And I think that's basically backed up by what you see with the high quality images for OSC when it's done properly sampled. Okay. And so for those of you who aren't believers yet, did everyone get a good chance? I don't know if this video came through cleanly across the web, but hopefully it did, that you could see everything kind of blowing out, right? I mean, this is 3 by 3 sampling. It's at the right scale for 2.4 arc seconds. By the way, I looked at the specs. I looked at the specs of that camera and against the telescope, and that is 2.4 arc seconds. So that's why I used that, okay, so that you could see how the colors are being spread on the grid, right? Okay, so now for those of you who might not be convinced yet, okay, let's have a quick sidebar on dispersion, all right, and ask you, for those of you who are particularly picky, how many of you image at 50 degrees or lower in elevation? Because if you image at 50 degrees or lower, your blue pixels are offset by 1 pixel or more upwards towards the direction of the zenith. And if you image at 25 degrees, okay, your green pixels are offset 1 pixel. Your green data, all right, that you're hoping to be perfectly positioned in that 3 by 3 grid is offset by 1 pixel upwards towards the zenith. And if you're, silly enough to be imaging, okay, maybe you have to go south, all right, you have no choice. But if you're silly enough to be imaging at 17 degrees, your red pixels are shifted down towards the horizon 1 pixel. Your green pixels are almost 2 pixels off, and your blue pixels are not even in the same 3 by 3 grid anymore. Your blue data is all the way over in another 3 by 3 grid. Okay, so let's just be reasonable and rational about the arguments we want to make about how much fidelity we need when we're talking about 1 or 2 pixels of fidelity. Okay, so let's switch gears for a moment and talk about color noise. Because this is also a real impact. The difference between mono and color shows up in that you've got two green. Everyone who images in one-shot color knows that this is what it looks like when you get integrated. You have a lot of extra green. And if you want to get that color balanced back to neutral, when you do your background neutralization, something's got to give, okay? So green either has to go down in signal, or typically what's done, I think, is that they raise the red, they scale up the red and the blue signal until the white balance is proper. And that's typically done with SPCC or some other color calibration. But, when you do that, if you scale blue and red up, you bring the noise with it. Okay, and so you have less signal in the red and blue channels, and it comes along for the ride. You also have more noise, and so when you scale that up, you bring the noise up with it. This is real for OSC. This is a problem because you are gathering less red and blue signal than what you would be if you were doing it with OSC. But the saving grace is that you do have some mitigations for this. All right. Things like noise exterminator are very good now at reducing that. And you also have the ability, you can always take some more data to try and level the playing field for your red and blue data as compared to what you would have received with mono. Okay, so let's put all of this together and let's talk about kind of the factors that are in play here. If you're using OSC, you really do need to dither and drizzle. If you don't do that, mono is definitely going to retain an advantage over you, a color resolution advantage. On sky, when you go on sky, the seeing cell is going to blur everything out, and it's not going to be that much of an advantage. But you still have, you still should be doing dithering. There's good reasons to dither, by the way, anyways. Everyone should be dithering, mono and OSC, for other reasons. But if you're OSC, you have more need to dither than a mono does. Mono definitely has less color noise due to that scaling down of the green and scaling up of the red and blue. But like I said, you have noise exterminator, and you can always take some more subs to sort of balance out that problem. When you sample 3 by 3 over the seeing, that spread of color in the cells is going to make V and G interpolation work well. But if you're not a believer in that and you don't want to even deal with that problem, just drizzle, right? Drizzle completely eliminates um, the interpolation problem. You don't do interpolation when you drizzle because you're basically getting to sub-pixel resolution by shifting the array around, and then color is reconstructed from the smaller subpixels directly without having to do an interpolation kind of process. So you get to full potential resolution, equalizing your mono and OSC. Finally, always try to image at high angles. Yeah, that should be obvious to everybody. But if you are stretching your your ability and going down low, you really are hurting yourself. And any problems that you can imagine, if you're picky about things like interpolation, believe me, Bayer color interpolation is going to get dwarfed by the problems associated with uncorrected dispersion. Okay, so now I'm going to switch to efficiency. All right, and we're all gonna be Einstein for a moment, and we're gonna play a mind experiment. Yeah, we're gonna ask ourselves, let's do a 4-hour test comparison. Okay, mono versus OSC. And we're not really going to think about the transmission differences of the various color filters. We're going to assume for a moment that they're not too far apart. What kind of signal, what red, green, and blue signal would we expect to get from each camera in this 4-hour test? I'm going to give you a moment to think about that before I share the answer. Okay, here's what I would come up with. All right. Well, 4 hours mono is pretty easy because I'm just going to divide 3 filters, okay, by 4 hours. And I'm going to say I should get 1.33 hours of red, the same for green and the same for blue, right? I just divided, 3 filters in 4 hours, and that seems to make some sense. Maybe it's not so obvious, okay, how you might get to the OSC answer. But if you think about 4 hours, I've got 16 pixels here. 1/4 of those pixels are red. 1/4 of those pixels are blue, and 1/2 of those pixels are green. So if I've got 4 hours, well, 1/4 is 1 hour, 1/2 is 2, and I've got the same 1/4 for blue. So 1 hour, 2 hours of green, and 1 hour of blue. So if you want to think of it in f-stops terminology, that's not very big. Mono has a plus 0.4 f-stops for both red and blue, and OSC has a 0.7 f-stops advantage in green over the mono. So that's not a bad guess, actually. That kind of gives you a warm fuzzy for where to start. But the question is, can we do better than this? Can we define how it actually works? And I think we can do better. So what I'm going to do is I'm going to do a spoiler alert. Okay, I'm going to give you the answer first, and then we're going to explore why the answer is as it is, and hopefully you'll agree with that. All right. So here's the myth. The myth is that mono efficiency is always higher than OSC. And the reality is, this has been hotly debated. And I would say it's been reasonably conclusively resolved. Okay, they've done this with calculators. All right, and so efficiency turns out to be dependent on the kind of imaging that you're doing. If you are doing mono, luminance plus RGB, that's always more efficient than OSC. The more luminance you take, the more efficient it is. And you can say, why? Well, because luminance has very high transmission as compared to R, G, and B filters, which are blocking some of the light, right? And so, yeah, you're always going to win when you're taking luminance data. However, the less luminance you take, the closer to parity you can get, or even crossover compared to OSC. And you might say, well, why is that? Well, before I get there, I'll tell you that mono RGB, okay, without L, can be less efficient than OSC. Now that's very counterintuitive. You wouldn't come up with that idea, but the calculations sort of uh, basically make that a reality. And why? Because monofilters have very sharp and narrow bandpass overlaps, right? This is one reason. And monofilters also sometimes have light pollution gaps where they're not catching any of those photons. And that's needed for light polluted environments, okay? But it's a hindrance in dark skies. And so again, this is somewhat dependent on where you are, right? Are you in a dark sky? Are you in the city? If you're doing mono RGB without L, you can sometimes get less efficient than OSC. All right. So now let's maybe try and understand a little bit better why this is as it is. If you go online and you start looking for Bayer matrix pictures, you're going to find a million pictures that look like this, okay? Where the red photons come through the red filter and get counted as red electrons, the green comes through, the blue comes through, and all the other wavelengths are rejected. Yeah? Do you remember this picture I showed at the beginning of the presentation with the Bayer filter? Look at what the text says. A filter that passes only red, green, and blue colored light. Okay? Well, guess what? That's not how a Bayer matrix works. Okay. So the first thing we have to understand is a little bit how the Bayer differs from the color filters. And we're going to forgive the mono imagers for a moment for thinking about how this efficiency game plays out. Because if you look at two very common filters, an astronomic and an optilong, you can see that we do in fact have high efficiency, okay, up in the 90, but we have really sharp cutoffs here with minimal overlaps. Here's a case where we have no overlap at all. We're actually missing these bands. This is light pollution filter, okay? I mean, you need that in the city, but you don't need it in the dark. And this is the optilong where there's no light pollution gap, but again, sharp rises and cutoffs, minimal overlaps. Now compare that to a Bayer matrix. Wow. Huge different game. Now, to be fair here, we're looking at relative response. This is not 100% efficiency. This is a relative response. Blue is 80% of what you get in green, and green is not 100%, okay? So they don't typically tell you what the Bayer matrix is, but you can find it with some pain. But generally speaking, what we've got here is we've got very big overlaps where red is seeing green and green is seeing red. It's likewise for blue is seeing green and green is seeing blue. And this is a whole different kind of ball game as compared to a mono filter. Now, let's just say that it gets complicated, okay? Lots of people disagree on how much overlap is good, but I think we can make a couple generalizations that stick. And that is that if you don't have enough overlap, you can miss hues entirely, right? It's possible that you will not be able to make colors come out correctly. If you have too much overlap, you can get to color ambiguity. If the peaks aren't separated from each other in easy enough ways, you can lose track of some colors. The Bayer color filter array is patterned on your eyes. Okay, your eyes do very much the same thing. Look at green and red are extremely overlapped to each other. Blue is offset, but your brain sorts this out. And in fact, software can do the same thing for a Bayer matrix, right? Overlaps help to define cyan and teal and yellow, orange, brown hues, all right? But the second effect beyond the color is that it's not the case that these OSC pixels are not working. They are working. If you've got green data, it's showing up in the red, the blue, and the green pixels, okay? And this is true for all of them. Now, they're at a lower efficiency, but they are all working. It is not the case that a one-shot color camera the pixels are not working. They are working. All right, so somebody tried to take a 2600 mono camera and normalize the responses, the filter responses against a 2600 one-shot color camera. Same camera, just OSC versus mono. This paper is in the references. You can look at the paper if you like, but you can see that, the one-shot color definitely has lower transmission at peak values than the equivalent mono filters, but the one-shot color filters have much wider band passes than the mono cameras do. This looks like a light pollution filter here, okay, missing this gap, but notice in the one-shot color, it goes way over. And so what this person tried to do was add up all the area under the curve, and he took an approach to say that, well, the human eyes are only capable of seeing 3 decibels of signal differential. And so there's really not that much difference because I've only got 0.9 and 0.7 differential here, but blue he acknowledged was a little bit too high. It turns out I've seen other sources to say that the human eye is capable of seeing 1 decibel of signal differential. And so, this I think his final analysis might be a little wonky, but the idea, okay, of adding up the areas under the curve, this is a very good idea. And in fact, somebody has done that. What you can imagine a case where you split up these band passes into 5 nanometer sections and then do poor man's calculus on the areas under the curves to see what your photon conversion rate is in all of these bands. And that's exactly what was done with a calculator that was put out on cloudy nights. And the reference for that I'll give you. But this has been out there for years now, and I think people are slowly warming up to the idea that maybe it wasn't exactly as people were projecting. So I played a game with this, and what I did was I took a one-shot color camera with 5 time units. I'm using a 183 one-shot color and a 12-inch optic. That 12-inch optic is used in all 3 test cases. Here I switched to a 183 mono, and I've got a mono over here. So I've got 2 mono cases and 1 OSC case. I normalized the photon outputs here, okay, to 1. If you look at luminance, and what I did was I took 5 units of time for each of these cases, except in this case, I actually gave an extra unit of time just to make 2 R's, 2 G's, and 2 B's. And so 2 luminance gives you 43% more efficiency than the OSC. Okay, that's significant. That's a half a stop. All right, that's not too bad. Even with an extra time unit for mono, just doing RGB and no luminance, I'm only 88% of what I got in the one-shot color camera. So I think the bottom line here is that you can go out and you can play with this calculator. There's lots of filters, lots of cameras, lots of optics that have been put out there. You can go play with this yourself if you like and see if you can convince yourself that the idea is good or bad. But I think the math is solid. I think they did a good job here. So one lesson here is that although LRGB efficiency is always going to be greater than OSC, the reverse can be true as well. You can actually get yourself in places where OSC is more efficient than mono RGB. No matter how you slice and dice this, the energy or the efficiency differences between mono and OSC are not nearly what people are suggesting. 2 LRGB, okay, most people are not taking 2 LRGB, they're taking 1 LRGB, all right? But even if they were doing 2 luminance for every red, green, and blue they're doing, that's still only half an f-stop, okay? And let's keep that in the back of our mind, half an f-stop of efficiency improvement there for that kind of situation. Because we're going to come back to this in a moment. All right, so if mono versus OSC is not really about resolution, okay, if it's not really about color representation, because both of those can be equalized, and it's not really about efficiency because, okay, we're in the margins here. Signal to noise, yes, the mono has a little bit of an advantage. You do have a little more noise there, but what's the real issue? And I put real in quotes there because I want to ask you, how much perceptual color fidelity do you prefer in your version of reality, right? This is something that's not really talked a lot about, but what I've got here are 2 pictures. The real picture is on the left. That's the real picture. The one on the right, all I did to that picture is I took the picture on the left, I selected a very small wave band, the darker green, and I turned it purple. And now I've got this beautiful picture that's purple, and I can see some detail here that I wouldn't naturally have picked up on unless I did this. But this is what we're doing. We're with mono, we are changing our color palettes. We're twisting reality, and don't you think we're maybe inundated with enough false color? It's getting hard to tell anymore with, with generated images, what's real and what's not real. And so this is something to think about. How much color fidelity do you really want in your images? Would you show this picture to your, 5-year-old child and explain to them that this is real? Maybe not without telling them you changed it. Okay. Maybe to get close to concluding here, I'm going to talk about ChatGPT for a moment. I've had lots of conversations with ChatGPT over the last 4 months, okay, on this topic. And ChatGPT is like a voting machine. It will go out there and if you ask a question, what's better, mono or one-shot color, it'll first come back and tell you without a doubt, mono is better, right? Because it's parroting back what it finds on the web. But if you start adding to it more and more technical criteria, it eventually gets to the right answer. But you have to spend so much time doing it; it's almost worthless. And so, these are ChatGPT slides that came out, and basically what it eventually got there. It decided that colors like cyan, teal, orange, and warm yellow kind of vanish with a mono and filters. Perceptual color accuracy and fidelity is better for OSC. It told me that, where does this show up? Well, it shows up in galaxy dust, okay, oranges, yellows, and browns in the core in the core and the arms of the galaxies. It talked about planetary nebula, the aqua and teals that are real, but don't get shown in mono as often because they turn out to be blue with a hard cutoff on them. Where it really shows up and where I kind of agree is in the spectral gradient blends. Okay, so if you think about an emission and reflection nebula that are in the same field of view, uh, you get lots of mixing of energies, and that mixing of energies shows up in pastel colors, light pinks, purples, steel blues that you don't typically get when you get a sharp contrast cutoff in mono. Okay, so this is the kind of the trade space that ChatGPT came up with, and it looks like it's kind of a tie. All right, you're trading things against each other. In general, yeah, okay, I think I can buy into what they say here, but I don't think it's that interesting. Um, Let me give you my own conclusions. I said I would give you the good reasons why you want to do mono imaging. Okay. This is where I would favor mono imaging. If I were in light polluted skies, if I'm in the middle of Phoenix, okay, I probably want a good light pollution filter. And this is a place where mono is going to excel over OSC because OSC, I'm going to either have to put a filter on top of a filter or, I'm going to have to do other games to try and avoid saturation. And, it's just less ideal. I think in light polluted skies, the mono wins out. I think it's true that if you have a smaller, slower optical rig, if you already have that smaller, slower optical rig, and every second of time is SNR to you, the efficiency of mono begins to sort of have an impact, okay? I think this is a place where you don't have the option, right, of going bigger unless you want to buy another OTA. And so in that scenario for smaller and slower, I think SNR might actually make a difference. Sorry, mono might actually make a difference. If you want artistic flexibility, I mean, you're really into false color and you want to do narrowband isolation, this is the place where mono excels, right? If you want that artistic flexibility, yeah, that's the place. And if you want to do imaging in bright time, this is the game. I think mono excels there. Okay, but in a dark sky, um, the differences, that is the resolution, the color, and the efficiency, begin to balance out, or they might even swing towards favoring OSC because of those light pollution filters and the broader band passes where signal is adding up and being then deconfused by things like spectrophotometric color calibration. I want to say that remote hosting sites exist for a reason, right? I mean, dark sites are to be envied. Okay, yeah, you can do good work in the city, but you're giving up something when you do that. If you can get to a dark site, you're always better off going to a dark site. Atmospheric seeing is a great equalizer. Yeah. Anything you could do in the lab, all right, gets kind of washed away by that low pass filter that we call and love our atmosphere. Saves us from X-rays and cancer, but is hurting us in other ways. And so you can mitigate everything that is happening that's advantageous in the lab by going out under the skies and or doing some processes like SPCC, noise exterminator, or drizzle. I want to say that your site conditions, the way you capture your technique, and your post-processing tools and skill are going to have a lot larger impact on your results than whether you chose mono or OSC. The fact of the matter is, both camera types can yield great results in skilled hands. And the fact, again, that that people are arguing back and forth, these are two heavyweights going at it, but there isn't that much differentiation between them. The fields can be leveled between them, and so a lot of this is unnecessary fighting. I will say this: pick your poison, right? Ultimately, we're all going after details like resolution, and the signal to noise matters. So I'm going to come back to that original thought that I gave you. Compare an 8-inch Hyperstar OSC that is probably cheaper to buy than a 4-inch f5 Takahashi, okay? That OSC is going to have an SNR that's 5 times greater. So yes, it is true that the mono camera is more efficient by a half focal stop, but your full advantage, okay, is way greater. You've got a 27 times signal improvement, which remember, it's the square root of the signal, okay? So you've got a 5.25 signal to noise ratio improvement by going to that Hyperstar 8-inch fast optical setup with an OSC as opposed to the mono, even given dithering and less OSC efficiency. You're still going to come out ahead. And so I think if you're starting from scratch and you can get to a dark site, you're not limited by other factors like I can't carry the OTA, or I can't afford the amount or whatever. I think you can do better, probably outperform the smaller, slower system with a bigger, faster system. And finally, I do think it's important to consider the real trade. A lot of people now, we are in fact being inundated with false color images of these physical phenomena. And if you like that, false color clarity, then mono is going to win. If you want physical fidelity, that is, if you want to see hydrogen in its real energy color, you need to see that with OSC, because what we're doing with mono is we're mapping the colors. We're not exactly producing the right colors, and instead we're mapping them in ways that isn't real, and the public is coming to believe that those are real when in fact they aren't. So do you care about perceptual color fidelity, or do you like the artistic allure of the clarity better? All right. So with that, I will leave this up for just a few seconds so that it's on the recording. And if you want to, you can go back and look at it. But the paper that I showed with the various 2600 filters and the calculators out there in the one-shot color by the numbers, please. There's a bunch of nice references here that you can go back and look at. And so I'm going to leave you with a question. Which of these pictures is mono and which of these pictures is OSC? Anyone want to venture a guess?
I'm gonna go. I'll say the one on the left is mono.
I agree.
Okay. Anybody else?
I'm going to go with mono on the left also, because it seems to be poorer to my perception. And from what you're saying, I'm beginning to think OSC has got pretty good advantage sometimes.
Okay.
I would say that the one on the right, if they've got a whole bunch of luminance, is probably the mono, because if you take a lot of luminance, you're going to have a lot more stars.
Okay. So let me give you the answer. It's a trick question, all right? You should never, ever do this. You should never compare post-process data against each other. Okay, that's really unfair because you don't know what nights this data was taken on. You don't know if the scopes were exactly the same, or there's too many variables in play to answer the question properly. But having said that, I can tell you that there is a couple hints, and the hints were in the talk. Okay, and so look again at the colors. Don't look at the resolution, okay? Because again, this could be a seeing difference. It's not about resolution. Remember, both camera types have the same resolution. Look at the color representation. If you look at this one on the left, you can see that in certain sections, okay, where the emission and the reflection are bumped right up against each other, you've got mixing, and hues are in here that do not appear over here. If you look at the pinks here, you can see that they're very stark, okay? They've been saturated, but there's not a lot of hue differential in the middle of this cloud here. Toby's right. The picture on the right is the one-shot color, and you can see it in the colors. The blue has less hues of mixing, and the pink has less hues of mixing than what you get with the OSC. Here, the energies are being represented a little better because this picture was taken in a dark sky where the broadband band passes of the one-shot color camera are wider and are capturing that data better than what's happening here. This may have more contrast. It's more contrasty, okay? But there are fewer colors that are actually in this picture than are in this picture. Does that make sense?
Doug, I
Yeah.
think I maybe misunderstood something. I think you contradict yourself on which one was one shot and which one was.
This is the one-shot color on the left. This is the one shot. This is the mono on the right. If I
Got it.
didn't say that, that's what it is. I said Toby was right, and Toby, if I recall, said that this is the mono picture, and it is the mono picture. Okay, but you can tell the giveaway now. Once you start looking for this, you can see it everywhere. Okay, you can see the difference between when you look at these very contrasty images. If you're looking especially at nebulae, you can begin to tell, wait a minute, I think there's more energy mixing that's going on in here, and all I'm seeing is stark contrast. I've got some hard cutoffs that are occurring, and I might be saturating, and the overlaps allow me to get some hues in here, but not as many as you would get if you have a broader bandpass. Okay, so I'll open it up now for questions. And I'll give you just another example. Okay, I think this is a much more obvious example of which one is mono and which one is OSC. But as you begin to look at these pictures more, you can begin to tell what you're getting. All right, and so I'll leave it to say that this is a trade space. There are times when you want to use mono, right? There are conditions, site conditions, when you want to do that. There are other times where you're giving something up to do the mono, and you ought to ask yourself, is it worth it? Both from a money perspective and from a reality perspective. Okay, so I'll leave it there and I'll open it for questions. If anybody has any, I'm glad to answer.
I do have a question, and it's more around dithering that
Yeah.
you had mentioned towards the middle of the presentation. So I know you had mentioned that everybody should be dithering with their camera. However, something that I have always wondered about that is just the inaccuracies, I'll call it, of the system just guiding on a sort of like when you're using PhD and you're guiding, it seems like it's just naturally dithering anyways. I don't think I have to tell the to go from frame to frame to tell it to dither every 3 frames or 10 frames. It seems like you get it naturally with just the variability of the system taking the images as it's tracking to the sky.
Well, okay, so the question is your guiding poor enough so that your dithering gets you to another 3x3 grid? Are you at least 1 arc second off when when you're doing your bad guiding? All right, and I think the answer is probably, hopefully not. Okay, so for the most part, it is true that you might be dithering by a pixel, but that's not, generally speaking, quite enough to in bad guiding to do the job. You really want to be dithering by several pixels, enough to get you into another 3x3 pattern. Okay,
Okay.
I'd say that, and there are good reasons. Even again, if you're doing mono imaging, you should be dithering as well. There are calibration reasons why you want to do that, right? So.
I think you can make a good argument that the dithering should be a prime number of pixels. I think that would be a significant contribution.
I don't know. I guess I haven't thought about that, but I haven't thought about it enough to comment on that. But certainly, some number of of pixels to push you into other patterns is important, and for OSC, absolutely required. You are not going to recover true parity in your against mono color resolution unless you dither and drizzle. That's a requirement that dithering or that mono doesn't have the same requirement for. You both have reasons to dither for other purposes, but in the OSC case, if you want to,
Why do you say prime number? I set my stuff up to 10 pixels and it's random. So I'm not sure why I understand a prime number.
I was thinking of the Bayer mask. Basically, it's a 2 by 2 grid, and so if you move by 2 or 4 or 8 pixels, you're really just falling on the same pairs, unless
yeah, you
obviously a
definitely don't want to
diagonal,
fall
then
in the
that would
same.
be different.
Yeah, you definitely don't want to fall in the same pattern. But again, you also don't want to be 2 by 2. You want to be 3 by 3. Yeah. You want your
Yeah,
sampling to be 3 by 3, and
okay.
then you want your dithers to get you over into another 3 by 3. And if you're constantly randomly dithering so that you're always moving to another 3 by 3 pattern, you're going to be in better shape for interpolation, but really you want to be drizzling.
Yeah.
But one thing we didn't really talk about it, one of the big trade-offs for me is time involved with acquisition and processing. I mean, we're talking about at least 4 times as long, right? With mono.
No, I don't think so, because again, that's the common myth that it has to be 4 times as long. It doesn't have to be 4 times as long because again, your green pixels are getting red data and your blue pixels are getting green data. And so you're getting more signal. Spectrophotometric color calibration then unravels that problem so that it treats that extra signal as essentially luminance and then puts a white balance on there that basically corrects for that. You do have more noise, but you do not have to image for 4 times as long to get the same data. Yeah. However, okay, this is back to the, if that really is a concern to you, then I'm going to ask you, why did you choose and I don't know that you did, okay, but I'm philosophically we're asking, why did you choose a small refractor and and a slow optical speed in the first place? If you really know that time is of the essence, I would say go after that big, fast, 8-inch F19 hyperstar with an OSC. Now you don't even have to worry. You've got photons, that are coming out your ears, right?
Well, I do have an SCT, but I've yet to do the Hyperstar. I'm
Let me
that
tell you,
direction.
there's some real truth to that. I've got more photons than I know what to do with. And in fact, if anything, it's a liability because now my camera saturates so fast, I can only take 45-second exposures before I saturate. This is how
Right.
fast the photons are coming. And so, if you're really worried about time, buck up and, and get yourself a fast, larger, faster
Right.
optical train.
Another fascinating thing is the same camera. You mentioned the ASI 2600
Yeah.
mono versus color. Why they're effectively the same camera without one width and without the Bayer
Right.
matrix in it. Why is the mono camera more money? You would think it's less.
Because again, the perception out there is that that mono is more efficient, and it's true. There is some efficiency associated with that. It's cheaper to put the Bayer filters on there and produce them. But yeah, there's really not a great reason why that should be the case, that the mono camera is more expensive, because it is exactly the
Yep.
same micro lens, the same amplifier and digital readout circuitry. So it's just adding the Bayer matrix, and you'd say to yourself, well, that should cost more. But
I
whatever.
I
dare
think
say,
it's volume based, really.
It
I
Yeah.
could
mean,
be.
how many
Yeah.
mono cameras do they sell, really,
Yeah. But I
compared?
don't know, even then, if you think about it, I don't know, the number of monocams versus the number of OSCs, I would think that's not that different, but I
Yeah,
don't
but
have any facts to back that up.
yeah, but they're selling
don't
cameras
those
into,
sensors also go into cameras, regular
yeah,
terrestrial cameras?
Yeah. You mean the Bayers?
Yeah.
Yeah, no,
So
for sure. Absolutely.
they'll sell 100,000 of those to every
Right.
100 of the monos.
Right. So maybe, okay, I see the reverse logic that you're using here. Maybe it's the case that because they have to make these other cameras special, they charge more for them.
Right.
it's a business question.
Yeah,
business, not a technical issue.
right, exactly. Okay, anything else? All right, well, I've enjoyed giving the presentation. I hope you guys, you know, see into this, that it's not cut and dried, that you can balance the playing field, in multiple ways, either with the different optical train or by doing some methods, like drizzling and SPCC, noise exterminator, right? There's multiple ways to skin this cat and level the playing field a little bit better. I think the only thing you can't really do is you can't recover colors that haven't been passed through a filter bandpass. And this is maybe the one weakness of mono, that if it matters to you, if seeing your green colors, which are the true colors, as opposed to the blue, if you really like the blue artistic thing and it doesn't bother you that O3 is green, and you've displayed it as blue, well, then good enough, right? Call it good. If it bothers you, then then the one-shot color is probably the way to go.
No, I appreciate this, Doug. Just one question for you. Which one are
Sure.
you shooting now, mono?
I shoot in color because it's very important to me. Why I liked the hobby in the first place and why I was a professional. I'm interested in the science and I like the physics. And so to me, I want to see the colors of the physics, right? I think it is important to see those represented accurately, and I do a lot of outreach. And so from that perspective, when I show the public my images, I want those colors to be real. I don't want to have to be constantly explaining that I did false color mapping. I want them to see the colors as they really are. And I think there's something divine about, seeing the colors as they really are. That's just a personal preference.
So in that, Doug, do you use like any HA filters or anything like that when you're try to get some of the hydrogen alpha in there, or do you
I
just strictly
don't.
just okay?
But okay, I will say that hydrogen alpha is a little bit of a slippery slope because the color camera's sensitivity, relative sensitivity to the other channels, is appropriate. And so when you see these color images of HA overlaid on top of the galaxies, typically what they've done is they've boosted the HA by at least 10 and sometimes up to 100 times what the real values are. And so, it's a slippery slope. How far do you want to go to say, I want to go get that HA signal and overlay it on top of my galaxies without boosting it so far that I have to explain that it's kind of fake? That trade space is, nebulous. It's slippery slope there. Although I have thought of doing it, believe me, and I probably will do it. Okay, so I'm a practical person. I would like to see the HA there, but I think I would probably keep it somewhat muted, in the same way that I personally choose to saturate my images a little less than what most people do, because I think maybe some of the saturation we see on the line is a little bit aggressive.
Thank you.
All right, are we there?
Think we're
I
there?
don't know how we did for time. I totally lost track of time. I hope I didn't keep you guys up to midnight. Okay.
No, hour and a half, perfect.
Okay,
Loved it.
great.
It's great.
All right.
It was
Super
nice meeting all
discussion.
of you.
Thank you for
Thank
inviting
you
me.
very much.
Thank
Thank
you.
you. It was a
Thank
great
you.
talk.